Greetings to all. We will continue with the remaining topics of the SFM reconstruction or the structure from motion reconstruction. In the previous lecture class, we were discussing about the basic concepts of structure from motion, and we discussed the three cases. So one case is the internally calibrated perspective camera, and equivalently that gives us a Euclidean structure from motion. And the second case is the uncalibrated weak perspective cameras, which give us an affine structure from motion. So we had discussed some basics of that. Now we'll go through a step-by-step procedure of how we can reconstruct using the affine structure from motion problem. Okay, so there are two steps involved in that. First is that we can compute the affine shape, okay, and also the corresponding projection matrices. And the second step is that in order to convert or rectify this fine shape into the Euclidean space, we can put some additional constraints regarding the known camera calibration parameters can be put in order to obtain the rigid Euclidean structure from the affine structure which has been obtained from the affine SFM. Okay. So now how do we go about with the affine reconstruction, right? So in order to understand how the affine reconstruction is done, we need to know what is the affine equivalent of the epipolar constraint. So earlier we had discussed about the concept of epipolar geometry and about epipolar constraint, but that was in the context of the Euclidean transformation of the Euclidean space. So now we will just quickly see how we can find out an affine equivalent of the epipolar geometry. Okay, so this is also called as the affine epipolar geometry. So let us consider that we have two affine images, right? So if we have two affine images, we can write the corresponding projection equations as given over here. That is, given A and B are the parameters of the affine transformation, I can write P is equal to AP plus B and P dash is equal to A dash B plus B dash. So remember, P and P dash are basically the image correspondence pairs, and capital P is the 3D point, right? So just like how in the case of Euclidean space, I write it as X is equal to MX, capital MX, okay, where this is the image, this is a 3D point, and this is basically the camera matrix M, right? So same way, instead of X, it's just a different notation where I'm using P dash, and here instead of the camera matrix, we are, since we are what we're considering is an affine camera, we use A, B and A dash B dash parameters. Okay, now this set of equations, now what we are discussing is from the two images. Okay, in the case of two images, so when you are considering two images, what I can say is here you can write this system in this form, this equations in this form. That is, I can just rewrite this as A, P minus B, A dash, B dash minus B dash into P minus 1 is equal to 0. Right. So when I'm working with affine epipolar geometry, what I mean, or what it is intended, is that the camera that I'm using is an affine camera with the camera centered at infinity, right? And this is the corresponding equation that I have for the projection matrices of the camera, and the projection equations with regard to the affine camera. Okay, now one necessary and sufficient condition for these equations to give a non-trivial solution is that the determinant of this matrix that we just saw should be equal to 0. Okay, so that in order to ensure that the capital point P that we are trying to reconstruct is not 0, or it is not at the origin, right? It would be somewhere else, right? So in order to ensure that it gives us a non-trivial solution, we can use the condition determinant of the matrix is equal to 0. And equivalently, I can also write this expression in this form. That is, if I assume alpha, dash, beta dash, and delta, okay, to be certain constants which are related to the matrices A and B, then I can write it in this form. I can write this determinant of the matrix is equal to 0 as alpha x plus beta y plus alpha dash x dash plus beta dash y dash plus delta is equal to 0. So what that means is you're just trying to equivalently write it in a form of a linear equation here, right? And remember, xy are the coordinates of the point P, and x dash y dash are the coordinates of the point P dash, okay, image points P and P dash. So once we know the image point correspondence pairs P and P dash, I can easily find those values. So the unknowns that I have is alpha, beta dash, beta dash, and delta, right? So here, this is what you call as the affine epipolar constraint, okay? And here I can further just rewrite this equation as alpha dash x dash plus beta dash y dash plus gamma dash is equal to 0, where gamma dash gets this value, okay, that is alpha x plus beta y plus delta is equal to 0. So what I'm doing is these values which corresponds to the constants which corresponds to the image point P, okay, and the constant term, we are trying to group it together to write it as gamma dash, and therefore I can write it in this way, okay. So this is what you call as the affine epipolar constraint. Now, in the case of affine epipolar geometry, what we observe is that the epipolar lines L and L dash, it will be parallel. Okay, so if you see over here in this particular image, what you see is all epipolar lines will be parallel to each other. Okay, so that is one property of the affine epipolar geometry. Now, again, just like the previous case, in the previous case, what we saw that we can write given a point here x, f, so f x dash is equal to 0. We can write it in this general form, right? In the case of the Euclidean epipolar geometry. So in the case of affine epipolar constraint also, you can write it, you can use the same type of expression where you can write xy1 f x dash y dash 1 is equal to 0, where xy1 represents the homogeneous form of the point P, x dash y dash 1 represents the homogeneous point of P dash. So there's a transpose over here, right? And here this F is what you call as the affine fundamental matrix, okay? And the affine fundamental matrix in this case, it takes a different form. Now it has got parameters alpha, beta dash, and delta, right? These are the parameters which are associated with the affine geometry, okay? And the fundamental matrix can be written in this form. Okay, so here when we come to affine weak calibration, okay, so basically when you're working with an affine reconstruction or an affine SFM model, okay, there all the weak projective space denotes the affine construction or the affine space, okay. So in the case of affine weak calibration, let's see how we can find the value or the unknowns or the value of the fundamental matrix F, right? So in order to find the value of F, you need to have n point correspondences which should be greater than or equal to 4. Okay, so you need to have at least 4 point correspondences PP dash. Okay, and so given that, let's say you have n greater than or equal to 4 point correspondences, I get a system of linear equations which is of the size n cross 5, right? So I have n cross 5 equations, and what I do here is I can solve it or I can write it in the form of uf is equal to 0, okay, and you have 5 unknown entries for that, right? So since you can write uf is equal to 0, in the sense I write all the known quantities, I arrange all the known quantities within the matrix U, and I arrange all the unknown quantities within the matrix F, and I try to solve this UF is equal to 0 in the least square minimization form, right? So here U can be represented this way. I have x1, y1, x1 dash, y1 dash 1, etc. like this, depending upon how many point correspondences I'm having. And the value of f, or the contents in f, the elements of the matrix, the column vector f, would be alpha, beta dash, and delta. So these are basically my unknowns, which forms the fundamental matrix. Okay, so using uf is equal to 0, and instead of solving it as a system of linear equations, instead of solving it algebraically, what I do is I do a least square minimization approach in order to solve this uf is equal to 0. Now, after doing that, the affine, weak calibration looks somewhat like this. You see is that, these are the results of using the least square approach along with the Hartley's normalization. Okay, so if you compare this reconstruction with, or the calibration with that of the perspective model, you see that in the perspective model, okay, here if you observe this particular point in the case of perspective model as well as affine model, what you see is in the case of affine model, the 3D point which has been reconstructed. So all these circular regions that you see are the 3D points which have been reconstructed, and all these lines that you see, those parallel lines, are basically the epipolar lines, right? So we see in this case that the 3D reconstructed point exactly does not lie on the epipolar line here, okay, but in this case the point lies on the epipolar line. Okay, so what we see is that the affine weak calibration model, it gives more errors, or it is prone more to errors as compared to the perspective case. Okay, however, the reconstruction becomes easier. Okay, but the errors could increase with the case of affine reconstruction. And another point that you need to know is Hartley's normalization is very essential in order to get reasonable results. Okay, without the normalization factor, we are going to get very erroneous reconstruction. Now, from the image correspondences PP dash, what we do is we try to calculate the affine fundamental, fundamental metrics, and from there, what we need to do is we need to find out the camera matrices, right? So from PP dash, which are the correspondence point pairs, what we did in the previous step is we were trying to find out the affine F, which is the affine fundamental matrix. From this, now we need to find out the camera matrices M and M dash. Okay, and let us see how we can find the camera matrices here. So if you look at this particular equation, I can let me represent the camera matrix M is equal to AB and M dash is equal to A dash B dash. And let's say these are the solution, the camera matrices can be written in this particular form. Okay. Now, I can represent, as I said earlier, I can represent M tilde is equal to MQ. Now, let me, since I am doing an affine structure from motion, okay, as discussed earlier, if I am doing an affine transformation to the camera matrices, what I do is I get another camera matrix which is in the affine space, but which gives us the same image points. Okay, so irrespective, even if I'm applying affine transformations to the camera matrices and the 3D point, what happens is the image points that I get will be the same provided it's within the affine space itself, or provided it's an affine structure from motion reconstruction. So that means in the case of affine structure from motion reconstruction, the image points are invariant to the affine transformations on the camera matrices, right? So let us assume that Q is some arbitrary affine transformation, okay? If that is the case, if I'm applying that affine transformation to the camera matrix M, I get M tilde. And if I'm applying that to M dash, I get M tilde dash. And this M tilde and M tilde dash both gives us the same image points as M and M dash. Okay, so this particular property, we are trying to make use of this particular property in order to solve for this problem of finding the affine structure from motion. So what we are going to do is we are going to transform the camera matrices into a certain point that will help us with easier calculations, okay, by carefully selecting the value of Q. So Q in general, the matrix Q can be written as CD01, right? Now what we are going to do is we have to select the values of Q in such a way that these projection matrices M tilde and M tilde dash is in the canonical form. Okay, so what canonical form means is I choose a value of Q in such a way that I'll get M tilde, I can represent M tilde is equal to 100000100. I can represent it in this form. That is somewhat like an identity matrix followed by zeros. Okay, that means I do not have any unknowns in M tilde, and all my unknowns which has to be computed goes to M tilde dash. So my M tilde dash can be represented as 0010 ABCD, and where these ABCD are basically the unknowns that I have. So what I'm trying to do is I'm trying to select a transformation matrix Q, okay, which is an affine transformation, or which represents an affine transformation, such that when I'm applying this affine transformation on the camera matrices, I get it in the canonical form, which is given by M tilde with no unknown quantities and M tilde dash with all the unknown quantities. Okay, so writing in this way actually helps us with reducing or simplifying with the processing steps. Now what I do is, let's see how we proceed with solving this. So this is the general expression for the camera matrix. M is equal to AB, and I have M dash is equal to A dash B dash. So this is with respect to the first camera. This is my second camera. And remember, we are talking about two image views only in this case. And I have the 3D point P. Okay. Now, my first step is that I do an affine transformation in such a way that I can convert it into the canonical form. So I get the camera matrices now transformed to M tilde, which is given by this equation here, and M tilde dash, which is given by this equation, which has got all the unknowns that we have, right? So we know that M is or M tilde both can be represented in this form, where I can write it as A is in the matrix form and B is basically a column vector, right? So this equation or this particular matrix that I have can be again decomposed as a 3 cross 2 matrix, 2 cross 3 matrix and a column vector over here, right? So I can write A tilde is equal to 1000010. From here, this much part would be my A dash or A tilde, and this column vector, the last column vector, would be my B tilde. Similarly, I can decompose this M tilde dash also into A tilde dash, which is this one, and B tilde dash, which is my column vector here, right? So this is trying to represent the cameras in this form is what you call as canonical affine cameras. So these are affine cameras, and in the same way it's canonical because one of the cameras do not have any unknowns over here, or you can say that it is kind of normalized, whereas the other camera parameters has got all the unknowns. Okay, so what we do now is, now the next problem is for us is to calculate or to try to find out these unknowns A, B, C, D. So in order to find these unknowns A, B, C, D, we make use of the epipolar constraint. Okay, so how or what we do is, as we know that the epipolar constraint, these are the equations. I can write it in the matrix form, and in order to solve that or to get a non-trivial solution, I write determinant of that matrix is equal to 0, and then from there I get this equation, right? So this is something which you have already seen earlier. So now what I do is, when I'm trying to reinforce the epipolar constraint, okay, what I do is I can write determinant A P minus B is and A dash P dash minus B dash is equal to 0. Now we have already, by transforming the camera matrices into the canonical form or canonical affine camera matrices, I have found out an expression for A, B, A dash and B dash, right? So this is going to be my A, this is going to be my B, this much is going to be my A dash, and this is going to be my B dash, right? So substituting in the equation, and also we know the coordinates of P. Let the coordinates of P be represented by UV, and the coordinates of P dash be represented by U dash V dash. So in that case, when we substitute these particular values in this equation, I can simplify it in this form. I can write it as determinant of 100U, 010V, 001U dash, and ABC V dash minus D is equal to 0. Okay, so now this is the expression that we'll be working with, right? So again, when I find the determinant and solve it, I get it in this form. I can write it as AU minus BV plus CU dash plus P dash minus D is equal to 0. So now what you have is basically a linear equation, right? So since you have the linear equation, and these U and V are basically coordinates of P, U dash and V dash are coordinates of P dash. Okay, so this is corresponding to one image point pair, right? So since you have four correspondences or four unknowns over here, you need to have at least 4 point correspondence pairs in order to solve this as a system of linear equations, right? So what you can do is, you can go for, or you need to find out at least 4 correspondences, and instead of solving it as a linear system of equations, you can also solve it using the least square minimization problem. Okay, so in any approach, what you get is, you will get the values of A, B, C, D. You can compute the values of A, B, C, D, okay, if you have at least 4 correspondences. And once you know the values of A, B, C, D, I can find out what is the camera matrix M dash. Okay, and the camera matrix M is already known to us, because it did not, basically initially itself, it did not have any any unknowns. Only M dash had unknowns, which were composed of A, B, C, D. So that means now we know what are the camera matrices M and M dash. Therefore, the affine cameras can be computed, right? Now, next, what we need to know is how about the structure. That is how we can compute P, right? We have computed M and M dash. Next, what we have to do is, we need to compute capital P, or we need to estimate or find the reconstructed point P, right? So, in order to find out that, we know the affine epipolar geometry is given by this equation, right? A P minus B, A dash P dash minus B dash into P, capital P minus 1 is equal to 0. What we need to find out is this capital P. Now, if you look at this equation, once you have found out the camera matrices, that means the value of A and B is known to us from the first camera. The value of A dash and B dash is known to us from the second camera, and P and P dash are definitely the image correspondence pairs, and therefore those values are also known to us. Okay, so that means, since all these values are known to us, we can put in all these values in these equations, and therefore we can find out what is the location of capital P, right? So we'll get the location of capital P, or we'll get the coordinates for the reconstructed point capital P. So this would be how the after the affine weak calibration, this is how it might look like. Okay, so we have already seen this figure earlier. Now, if you look at the distance, the mean distance between the points and the epipolar lines, okay, so that means if you're trying to find out what is the error of the reconstruction, in this particular example, it is 3.24 and 3.15 pixels. Okay, so which is still large, and it would be better to even reduce that further. Now, one thing you can notice is that here the units is given in terms of pixels. If you remember, for the Euclidean structure from motion method, for that reconstruction, we saw that it was the error was written in terms, or it was expressed in terms of centimeters. It was around 10 and 9 point centimeters over there. Okay, so that is because since it is in the Euclidean space, the length is preserved, and therefore you can calculate what is the exact length. But in the case of a fine, the lengths are not preserved, and therefore we just go ahead with the pixels. That is, we just try to express the distance in terms of the pixels. Okay, and now the final step is, now that we have reconstructed in the affine space, we have an affine SFM model, right? Now the next final step would be to convert that to the Euclidean space, or to rectify. If you have to do some measurements, as I said earlier, if the lengths and angles and everything needs to be preserved, then you need to go to the Euclidean space, right? So how do we convert from the reconstructed object from the affine space to the Euclidean space? So if that has to be done, then that means there should be some mapping. A mapping should be found out from the affine to the Euclidean space, right? So here we can write, in the case of weak perspective projection equation, a general equation, I can write it as m is equal to 1 by z, k is 0, 1, r2, t2, right? So here r and t stands for the rotation and translation, which are the extrinsic parameters. K and S are basically the aspect ratio and the skew parameters, which are basically the intrinsic parameters, right? Now, if the camera that we are using is calibrated, so let us assume that if we are using calibrated camera, then in that case we can work with normalized image coordinates, and I need not I can assume these to be 1, in the sense I need not consider these within the equation. If it is a calibrated one, that means it is already known to us, right? So let us take k is equal to s is equal to 1 and simplify the equation. So then the equation just becomes 1 by z rt, right? And as we know, as we have discussed earlier, we can represent that as m is equal to ab, right? So if you look at this, what you can say is this a can be called as, or you can say it represents the rotation. Okay, and therefore, since a represents the rotation over here, or you can say it's a scaled rotation, if you remember, for a rotation matrix, we had discussed that, okay, for a rotation matrix, the rows would be orthogonal to each other and they have the same norm. Okay, so they'll be orthonormal with each other, right? So if you try to put in these knowledge about the rotation matrix, right, we can say, let's say the rows of capital A, the matrix capital A is represented by A1, A2 and so on. Then I can say A1 dot A2, since we're working with normalized coordinates, I can put a cap here, right? So A1 cap dot A2 cap is equal to 0, because the row vectors for a scale rotation matrix is orthogonal. And since they have the same norm, I can write it as A1, the L2 norm of A1 is equal to the L2 norm of A2 cap, right? So these constraints that we have can be actually put into the final equations. Okay, so these are the two constraints of the rotation matrix. Okay, so you can use that, or you can try to implement, rewrite the weak perspective constraints in this form. Okay, so where I write it in terms of C. Okay, so basically C is this parameter over here, which is a part of Q. So Q, as I said earlier, if you're doing a transformation in the affine space, right, it is invariant. The points that we have is invariant, right? So including all these parameters together, I can just write the constraints in this form, right? So once I have the constraints in this form, the unknowns that we have is basically the coefficients of C, right? So since the coefficients of C are the unknowns, in order to solve that, you can just use a least square approximation method and go about with finding the solution. So once you have the solution, what you need to remember is you are no longer in the affine space, but you have obtained a Euclidean reconstruction. Okay, and this is an example of how Euclidean reconstruction can be obtained from the weak perspective model. So what you're basically doing here is, okay, we are going ahead with finding the affine SFM or the affine reconstruction, and then we are using a least square approach to solve the system of equations that we had, and we are trying to rectify that in the Euclidean space. Okay, so here if I look at how much is the error which has been obtained using this method, you see that it's around 0.83 centimeter, or the in percentage it is around 3%. Okay, so now let us come to the third case where you are dealing with uncalibrated perspective cameras. So in the case of uncalibrated perspective cameras, the type of reconstruction we get would be a perspective structure from motion model, right? So again, the concept is the same over here. Only thing is that since you're working with the uncalibrated projective camera or perspective camera, that is basically in the projective space, these camera matrices M would be different. Okay, but the basic underlying approach towards solving this would be the same, where you assume that there are M cameras and N 3D points which needs to be reconstructed. So here again we can just write it in this general equation, xij is equal to mix. But here remember the camera matrix that we have here, this matrix corresponds to the projection camera matrix. Okay, it's a projective camera matrix. That means there is no calibration information which is known to us. Now here, if you look at how many points are needed or how many equations are needed, just like the previous case, you will have two MN equations. So where M is the number of cameras or number of images you have, and N is the number of points. So therefore, the total correspondences you have would be 2MN, and for MN correspondences, you will be having 2MN equations, right? And the number of unknowns you will be having would be 11M. In this case, because it's the projective camera that we are using, you'll be having 11M parameters. And 11 parameters for each of the camera. Then you have 3n, which is the 3 parameters for each of the 3D point, and you have to subtract minus 15, because just like how we discussed the case of the Euclidean and the affine space, if we are applying a projective transformation to the camera, the reconstructed points would give us the same image points as the first case, right? So in that case, we can remove the degree of freedom of the perspective, the projective transformation. And so therefore I get 11M plus 3n minus 15 unknowns. So that means you need to have at least 7 points in order to find the solution for a projective SFM. Now, in order to go about, or in order to find out the projective structure from motion reconstruction, there are basically three methods. First is the algebraic approach, that is by using or computing the fundamental matrix first, and it is very similar to the previous approaches we had. The second one is factorization method using the SVD, singular value decomposition approach, and the third one is the bundle adjustment. So we'll be seeing quickly about these three types of approaches in order to find out the projective structure from motion. So the first method is the algebraic approach, okay, which is found by using the fundamental matrix, right? So in the projective, SFM model, what we do is we are just trying to look at the case of two views or two images. The steps are exactly the same, where you compute the fundamental matrix and use it to estimate the camera matrices, and from that you try to estimate the 3D points using the epipolar geometry. Okay, so the basic steps remains the same. The difference is that the fundamental matrix that you're using here now corresponds to the fundamental matrix of the projective space. Okay, and the camera matrices that you're using is the projection camera matrices. Okay, and it's not just any camera matrices. So the equations also changes accordingly. Okay, so here we are making use of canonical cameras. So just like in the case of the affine space, here also while we are trying to do the reconstruction, we are going to convert the or transform the camera matrices into its canonical forms. We'll see how. So this is the general equation for the camera projection, where you have x is equal to capital M capital X. Now let us say H is the projective transformation. So if I'm applying the projective transformation on the camera matrix as well as the 3D point, what happens is the image still remains the same. Okay. Now let us say you have two views. We are taking the case of two views, which is M1 and M2, representing the projection matrices of the two cameras. And so I have M1 and M2, right? And then with M1 and M2, I'm trying to transform this. Okay, so that's why this H inverse is here. I'm doing a projective transformation to the camera matrices here, right? In such a way that for the first camera, I get it as identity matrix followed by zeros. That means I do not have any unknown quantities. And for the second camera, I can represent it as AB with all the unknown quantities here. Okay, so this particular type of representation or transformation of the cameras, we can call that as the canonical cameras or the canonical perspective cameras, right? So the similar concept was used for the affine case also, right? So for the perspective structure from motion also, we follow a similar approach where we are trying to transform this into the canonical camera form, right? The difference being that the transformation matrices that we are using would be a projective transformation. Now, next what we do is we need to solve for this, right? Now, how do we solve for finding the fundamental matrix? It would be the same as the previous cases, where given the projective transformation, when we are applying that to a 3D point, I get x tilde, right? Which is the transformed 3D point. Okay. Now, I can write x is equal to m1 h inverse x tilde, right? From the previous equation where we had m1 h inverse hx. The hx, I'm replacing it by x tilde, so I can write it as x tilde here. And since I have taken the canonical form, m1 now becomes I0, right? So or m1 h inverse becomes I0, therefore I can write it in this way. And since m2 is represented by all the unknowns, I'm substituting it by AB and then x tilde, right? So I get the equations of x and x dash in the represented by or in the form of the canonical camera models, right? Now, once we have this, and again taking this x dash, the equation of x dash, I can write x dash is equal to AB x tilde. Okay, so x tilde basically is it's a 3D point, it's a 3D reconstructed point, right? Now, representing that in the homogeneous representation, I can write it as x1 tilde, x2 tilde, x3 tilde 1, right? And since this matrix that you have AB, I can just try to decompose in this way. That is, I can write it as A into an identity matrix followed by zeros, x1 tilde, x2 tilde, x3 tilde 1 plus B. I can write it in this form. Okay, so this particular term or expression or equation gives me the same as this one. Okay, when I'm solving it. Now that I can write it in this form, let me just try to rewrite this x tilde into its previous vector form. I can write it as a I0, okay, x tilde plus b, right? Now I know I have this I0 x tilde, okay? So this I0 x tilde is nothing but my image point that I have, right? That means I can write this or rewrite this as ax plus b, because here this I0 x tilde we have already seen, this is my image point x, so I can replace that as ax plus b. Okay, so what I'm getting here would be, finally what I get is I can write x dash is equal to ax plus b, right? Now, we know that there's a property which says x dash cross b dot x dash is equal to 0. Or in other words, taking a vector, cross product of the vector with a quantity which is normal dot of the same vector itself would give me a 0, right? So trying to substitute the values of x dash over here, I can write as x dash, we have already found it to be ax plus b, so I can replace it by ax plus b over here, right? Now solving this further, I can write it like this is equal to 0. So when we solve this further, now again a point which we have discussed earlier, if I'm trying to find the cross product of two vectors a cross b, okay, I can represent that as a skew symmetric matrix, a multiplication of a skew symmetric matrix of A along with B, right? So I can write it in this particular expression also, representation also. So the previous equation that we had, we are just trying to replace it in terms of the skew symmetric matrix. So I can write it in this form. What I get would be x dash transpose bxa, which is a skew symmetric matrix into a, x is equal to 0. So once you have this equation, what you observe is that this is in the very familiar form of writing, x1 dash t f x is equal to 0, right? So therefore I can say this particular expression of skew symmetric matrix of B into A, okay, can be represented, or that can be denoted by the fundamental matrix. So that is basically denoting the fundamental matrix. Okay, I can say that because I get that equation from this particular general equation, right? So therefore what I'm trying to do is I find out the an expression for f over here, right, where I write f is equal to bxa. Now according to the epipolar constraint, okay, we can say that f dot e2 is basically the epipolar line, right? So I can write f dot e2 is equal to 0, or f dot e1 is equal to 0. So that means the epipole f dot epipole is equal to 0. Excuse me. Okay, so in this scenario, when we are considering A and B as a matrices, this epipole can be represented, or B, it is basically the vector B that we were discussing earlier, represents the epipoles. Okay, so since this is the epipoles, I can write, instead of E E2 and E1. Instead of E over here, I can just replace it by epipause. That means I can write f dot b is equal to 0. So if I'm writing f dot b is equal to 0, I have already computed an expression for f. I can write bxa dot b is equal to 0. Again, if I remove this from the skew symmetric matrix form, I can write b cross ax is dot b is equal to 0. Right? Now, I know that f dot b is equal to 0. Right? So that means I can compute the value of b over here as a least square solution of fb is equal to 0, right? And as I said earlier, now that you have the matrix over here which is represented by AB, since B is this value E over here, okay, now how you compute the value of A is given by this expression, that is minus skew symmetric matrix of X into F would give me what is A. Okay, A is computed in this way. So from this, after computing B and A, what I finally get is I can find out what are the projection matrices for the perspective cameras. So therefore, the perspective cameras are known to us. So this is how you calculate the perspective camera model, right? Now, how do you compute the points from the camera? So basically what you go ahead would be a triangulation model. So each of these steps, this has already been discussed. So from this we can try to compute the 3D point. Okay, so after the reconstruction, after the projective reconstruction, this is how, or this is an example of how the image may look like. This is just one example. Now in this particular example, what we see is the error that you have is around 0.34 centimeter, or the error is 1.2%, and we see that the error has reduced considerably in this case. Okay, so the second method is the factorization method. So in the previous method, which is algebraic approach, the approach remains exactly the same as that of the Euclidean SFM approach. The only difference is that the fundamental matrices that you're considering, as well as the camera matrices that we're considering, all takes a different equation, that's all, but the approach remains the same. In the second approach, which is the factorization method by using the singular value decomposition, what you're trying to do is you're basically trying to factorize the matrices, okay, in such a way that it will help with computing for the unknowns, right? So we know that we can write x is equal to, I can write small x, which is basically the image point, is equal to 1 by z capital M, which is the camera matrix, into capital X, which is basically the 3D point, right? So here I can take Z to the other side. If I take Z to the other side, what I get would be Zx is equal to capital M capital X, right? So this is the same as that which is written over here. I can represent D, okay, which is basically my mx, the equation mx. I can represent that D as z11 x11, z12 x12, so on. So that is this zx is equal to mx. I can write mx in the form of a column vector into a row vector. Okay, so basically I'm trying to factorize this in convenient forms here, right? So if we know what are the depths z, then we could factorize d into m and s, right? Now, if we knew m and s, then we could solve for z, right? We can solve for this z over here. So what we do is we keep doing an iterative approach. That means we first assume certain initial values for z as well as ms. So with the initial values of z, we try to factorize d to estimate m and s, and from that estimate we try to solve for z, and again from that value of z we again try to factorize or estimate m and s, and we kind of do this iteratively. Okay, so we do this iteratively, such that the error keeps reducing. So this kind of an iterative approach is used when you are going ahead with the factorization approach. And the third approach is the bundle adjustment. So in the bundle adjustment, what we do is, this is the main equation for the bundle adjustment. This is nothing but an error term. Okay, all that we are doing is finding the error of the reconstruction. So here this X stands for what is the actual point, and this capital X or capital MX over here basically stands for what is the estimated point or the reconstructed point. And we tried, so this MX over here would be the image of the reconstructed point. So given the actual point and the image of the reconstructed point, we keep trying to reduce or minimize the error between these two. Okay, so it is basically a minimization problem, minimizing the reprojection error. Okay. So there are certain advantages and disadvantages in this, in this term where you're trying to, it's also called as refining the structure and motion over here. Okay, so the advantages over here is that it can handle a large number of views. That means it can take in a large number of camera matrices over here, and it can also handle missing data. But the limitations is that the minimization, because it's a minimization problem, as the number of views increases, the parameters also increases, and as the parameters increases, the minimization problems becomes bigger to handle. Okay, so sometimes we may not reach the global minima in such a case. So in order to ensure that the minimization approach is proper, and that we are going to reach the global minima, what you can do is you can use a good initial condition over here. Okay, so one such approach is that you can use any of the previous approaches for finding an initial reconstructed point or a reconstructed structure, and then from there you can use this bundle adjustment as a final step of SFM, where you're trying to kind of refine the structure and motion. That's why it's called as a refining problem. Okay, so having found out the reconstruction from any of the previous methods, we can use the bundle adjustment approach to just refine the method in order to reduce the error further. Okay. And using the bundle adjustment for the projective reconstruction, you see that for this particular example, you see that the error is 0.07 centimeter, or the mean error is 0.2%. So we can see how much the errors have actually reduced, and this is with 15 iterations. In the previous example that we saw, the error was around 1.2%. In this case, it has reduced to 0.2%. So bundle adjustment helps a lot with refining the SFM reconstruction. So now, once you have the projective SFM, you can rectify that to the Euclidean space, or you can rectify that to a metric reconstruction. So for that, you can go ahead with a stratified approach, where you go from the projective space to the affine space, and then from the affine space to the metric space. Okay. So again, most of the concepts is the same as that of what we have discussed before. So what we are going to say is that if you have a projective reconstruction and Euclidean reconstruction, this projective reconstruction and the Euclidean reconstruction can be mapped to each other using a projective transformation. Right, so there would be some transformation which can be used to map the projective reconstruction and the Euclidean reconstruction. And here what we need to do is we need to find out what is that mapping transformation, right? Or here we can represent it as Q. So now the problem reduces to finding what is this transformation matrix Q, which helps to transform from the projective space to the Euclidean reconstruction. Now, in order to find out Q, I can represent Q in this form. Let me represent it as Q3, Q4, where Q3 is basically a 4 cross 3 matrix and Q4 is a vector quantity. Okay, and here I can also write the camera matrix in the general form M is equal to rho K RT. Okay, so here rho is basically a scaling factor that you have, and K R T. K stands for the internal parameters, R and T stands for the external parameters, right? So if I'm applying this transformation matrix in order to transform from the projective space to the the Euclidean space, I can write it as, I can just replace for this M cap as MQ is equal to rho K R. So now if you know the intrinsic parameters, in the previous case, if you know these intrinsic parameters, I can assume that I don't need to consider this particular term or factor here, which is K, right? So that means I can write MQ3 is equal to rho R, or I can say that MIQ3 becomes a scaled, it is now a scaled rotation matrix. So if it is a scaled rotation matrix, you can make use of the properties of the rotation. So it is the same as that we have discussed in the affine space or the affine case, right? Where you use the properties of the rotation matrix in order to ensure that you move from the affine space to the Euclidean space. Here also we do the same, right? So when we are incorporating the properties of rotation space, or what you're saying is the constraints that we are putting is that they are perpendicular. The rows of the scale rotation matrix, they are perpendicular to each other, and that they have the same norm. So when we translate this, or when we try to put these constraints in matrix form, I can represent it this way. I get this set of equations where here this A is nothing but a matrix which is representing Q3, okay, or from which we can calculate what is the mapping transformation matrix. So therefore, from there, you can try to solve this as a least square problem, and then you can find out what is the, what is the final solution over here. So basically what you're trying to find out is, we are trying to find out this capital A, which is nothing but a function of the transformation matrices Q3 and therefore Q. Okay, so by finding A, you're able to find out what is Q, and Q is basically the mapping between the projective space to the Euclidean space. And we do this by finding or by using a least square method. Okay, so by this we come to the end of 3D reconstruction, and specifically the structure from motion reconstruction. So we've, as I said earlier, we've discussed about three different approaches, which is basically or three different cases, which is basically the internally calibrated perspective camera, the uncalibrated weak perspective camera, and the uncalibrated perspective camera. Okay, and we have seen how all of these are kind of similar to each other, how the reconstruction is similar to each other. However, the process of finding the fundamental metrics and the camera matrices and the way of representing them differ, as well as how it is being, how the affine and projective space is being rectified to the metric reconstruction also differs. Now, in the next video, we'll be discussing about the last topic. Thank you.